These are the two remaining lectures on the various mathematical tools that we require in the subject of fluid mechanics. I have already talked about the algebra of vector and tensor functions in my earlier lecture 5. Lecture 6, which is divided in two parts. The first part deals with the calculus of scalar, vector and tensor functions. Of course, both parts are on calculus of scalar, vector and tensor functions. In the first part of my learning objectives are learning the various calculus operations in generalized coordinates. So I've been stressing on that we must at least be exposed to handling any kind of coordinates or the procedures, though as I've told you that most of the time we keep using Cartesian, but there are a large number of still we will demonstrate in this course there are problems which you have to handle using cylindrical coordinate systems. So that's why the idea of general coordinate systems and how to handle various calculus operations should be there. So we will tackle this and in this part 1 of this lecture, and then we will learn about the del operator. What is this del operator? It is the most I should say very high utility operator in fluid mechanics. There are many physical quantities that are defined in terms of this operator, and the basic reason for this operator existing for this operator to exist is because of coordinate free treatment that we stress in this course. We should not be treating the various concepts of fluid mechanics without specifically taking the help of any coordinate system. That means the physics is not dependent on the type of coordinate system. So the physics and maths gets segregated if you start using the del operator. Now next two objectives are specific gradient of a scalar. So this you might have learnt in your some mathematics courses on offered by the applied maths department that you may have done till now. So in vector calculus you might have done gradient of a scalar. What does it mean and how you carry out the operation, and so I'll just do a quick review of that. And the curl and the gradient of a vector, this is going to be a little bit new to you. I'm not sure about the curl. Curl might have been taught again in vector calculus, but definitely gradient of a vector may not have been taught earlier. So all these operations, they give us certain quantities which are related to my local deformation rates and rotation rates that I have been talking about in my earlier lectures. Okay, well, the quantities which have been defined from kinematics of material lines, those are the quantities that you can express in three-dimensional coordinate-free forms using these kind of calculus operations, curl and gradient of a vector. So we shall show all that, and so this lecture is intended to be a slightly more elongated than some of my past lectures. So the request is to bear with me in this part 1. In fact, one of the reasons why I've divided this in two parts is because of the length of the lecture. Right. So I'll move on to the next, formally beginning these ideas. When we talk of calculus of scalar and vector and tensors, the calculus operations generally employed in the subject of fluid mechanics, they may be put into some categories. For example, I can talk in terms of two broad categories. The first category is the derivatives. which are of course the partial derivatives, because in fluid mechanics, space, time, both entities are involved, and every function or field function, you can say velocity fields, any kind of a distribution in the fluid continuum will in general depend on time and space. So we have these partial derivatives, del t and del xi. Xi here, I'm just trying to refer to some general coordinate system and a particular coordinate direction in that system, which I am designating as xi. Then I have the material derivative d capital D dt. This you have already learned in your first course in fluid mechanics. And then you have what I have been referring to as the del operator or gradient operator. This is also known by the name of gradient operator. But in our sort of discussion, I'll prefer the word del operator, okay, because gradient refers to a specific type of operation using this operator. So the name of this operator, I prefer to call it del operator, which is written as a inverted triangle, okay. So as you know, material derivative I've already written, I don't need to read it out. I mean, you know all this from your earlier course in fluid mechanics. And of course, material derivative can be of a scalar quantity like density, temperature, pressure, or even a vector quantity like velocity vector, or let's say a vector constructed by multiplying velocity with density. So all these things you already know. So then what I have written in red is how we use the del operator in fluid mechanics. All these quantities, gradient of phi and del dot v, del dot some tensor, and del cross v, all these are used in fluid mechanics. So we will be familiarizing you in this lecture with these kind of operations. Right now you may not be following what do we mean by del cross v, del dot tensor, and del dot vector, and grade phi, but of course you may be familiar with grade phi, but I don't think you may be following all of them. So that is the purpose of these lectures, to make you familiar with what do these operations mean, and eventually connecting them to physically meaningful quantities in fluid mechanics, okay. So this is the use of derivatives in four ways, as I've mentioned here. Two are direct, del t, del xi, and two are just combinations of all these time and space derivatives, the material and the del operator. Then the calculus operations, once derivatives are taken care of, then the other calculus operations are surface and volume integrals. That means both derivatives and integrals is what we call as the calculus operators. So the surface and volume integrals usually are used in this form. It means let's say v dot nds. This is already familiar. You are familiar. If you have a closed surface and you integrate the normal component of velocity on a closed surface, you get the volumetric flow rate through the instantaneous volume flow rate through the surface. And similarly, if you multiply by density and then integrate, you get mass flow rate. The second integral represents mass flow rate through some surface S. When I don't make a circle on the integral, it means it's an open surface. Otherwise, the circle means a closed surface. And similarly, you have some quantities like a tensor integrated over a closed surface, n dot t integrated over the closed surface. So this you may not be familiar, but what I'm trying to tell you is that quantities like this need to be understood, okay. So this is the purpose of these lectures on these mathematical tools and ideas which are so much necessary for any fluid mechanics student. Now, the last integral is a volume integral. So, first three were surface, then you do also have volume integrals. For example, if you've got a body force field intensity FB, you multiply by rho and integrate in a certain volume, instantaneous volume or region in the fluid domain, then you get the instantaneous body force acting on the fluid that is contained in the inside that volume. So this gives you the body force. So all these things will come later on also when we start developing the basic equations, but a little bit introductory mention here, that's all. Then we move on to the del operator, start our discussion from directly from the del operator, because as you will see, the ordinary partial derivatives I don't need to discuss, del t, del xi. You already know all those things from your earlier courses in mathematics and even fluid mechanics. And as you know, in the material derivative, we write the second term, which is the convective term, as v dot grad phi. So here also the del operator plays a role in the capital D dt material derivative. So therefore it's vitally important to just start talking about the del operator. So del operator can be used to define many types of calculus operations that can be used to represent or express quantities of relevance in the subject of fluid mechanics. So, for example, I've given an example here, so minus grad P or del P, that gives you pressure force per unit volume acting on fluid particles. So, this we have already seen in our second year course on fluid mechanics. Pressure force per unit volume acting on the fluid particles minus grad P. And we have already derived the volumetric strain rate, right? We have shown that del dot V or divergence V gives me the volume strain rate. Remember, we had derived it using the Gauss law and uh, taking the limiting value first, estimating the volumetric strain rate of a finite material region surrounding the particle, and then progressively examining the limit if the region was considered to be smaller and smaller. So we got this expression del dot V as the volumetric strain rate. But it remains to be seen how to handle this del in different coordinate systems. So that has not been talked about as yet. So this is what one of the objectives of the present lecture is. So the del operator can be written as, now notice, start paying attention to the discussion from this point onwards. I need your focus here. So del is just a symbol which is actually this operator. What is this operator? The operator is having a unit vector and a partial derivative written as del over del xi, and it is multiplied by 1 over hi. Okay, so you can read it this way, that ei del over del xi and pre-multiplied by 1 over hi. So this and of course the indicial notation you are already familiar now with the help of my fifth lecture where I talked and introduced this. So it means summation over I is implied because I is the repeating index. So this is a general definition in any coordinate system for del. That means if I want to write my del operator, whether I am working with Cartesian, cylindrical, or maybe even spherical or whatever, then I must start by writing it as this definition that I have written here. Now the natural question arises by what is hi and what is del xi. So first let me tell you what is del xi, as you have probably guessed by now. Del xi simply means partial derivative with respect to coordinate direction xi. So any coordinate system will have three coordinates for three-dimensional general discussion on 3D flow domains. You will have some coordinates x1, x2, x3. For example, Cartesian has x, y, z. You call them as x, y, z. And cylindrical, you call them as r, theta, z. Okay, three coordinates. So likewise, in general, we can say that a general coordinate system will have three coordinates, x1, x2, x3. So therefore, if you take any one of them and simply write it as xi, then del xi is the partial derivative along with respect to coordinate xi or the ith direction coordinate. Okay. Now what is hi? Hi, let us try to understand this in some depth. So what is hi? Hi is simply a scale factor. What is the scale factor doing? Scale factor is for displacement along xi. What do we mean by displacement along xi? Let me move to the next slide and we'll begin understanding all this. So in this next slide, I have told in red that del operator essentially is giving me what? It gives the spatial instantaneous rates of change of a quantity. That means you want to know that at a given instant of time, instantaneous means that if I am at a particular point in the flow domain and I move in any direction around that point, if I displace myself along any direction from that point, then for small displacements there will be some changes in the fluid properties or quantities that I may be interested in, and exactly how fast or what is the rate of change of the quantity with respect to the displacements. So since it involves del xi, so it means that along different coordinate directions it will give me how fast in space a quantity is changing locally at a certain point if the observer displaces himself along various coordinate directions or displaces along a general direction, let's say. So for general direction, that means he has to know the rates of change along different coordinate directions first, and then he can get an idea about any specific direction. I will show that how this is going to work. So this is what the meaning of del is, okay, written in quotes. Now, why use scale factors? Why the scale factors are there? Let's try to understand that. So, suppose I have some coordinate system. I'm not deliberately writing x, y, z or r, theta, whatever it is. I'm just showing three lines and a reference point O, and so I have a point P having a position vector r. Now, suppose I am displacing myself in space by a small amount, let's say from P, and the displacement is quite arbitrary. So it means delta r can be in any direction from P. So if I do that, then mathematically it's possible to write all these things in this way, that okay, point P has a position vector r, which can be in general written as xi ei. Again, summation over I is implied. So I need not mention this again and again, because by now you should train yourself to recognize repeating indices and the corresponding summations. So r can be written like this, and so delta r, just simply in simple terms, mathematics is very elegant here. Delta r means delta of xi ei, and therefore change in a product of two things can in general be due to changes in either of them. So therefore in the next step it's written as delta xi ei plus xi delta ei. That means change in xi ei can be brought about by changes in coordinates or changes in unit vectors. So this is something important, that delta r, the change in the spatial vector, that your position vector of point P for any arbitrary displacement, small displacement, that can be simply written in indicial notation and in any general coordinates, because I am not restricting to any specific coordinates. Delta r is equal to delta xi ei plus xi delta ei. Now we have already seen that what is delta ei. That means it is the change in ith direction unit vector due to the change in the coordinates. Now we have already talked about this with the cylindrical coordinates. I have already shown you that in cylindrical coordinates, some of the unit vectors, it's not necessary that all should change. Some of the unit vectors, maybe all may change, maybe some may change, but at least we know from cylindrical that er and e theta, they change with one of the coordinates theta. Okay, so it means that if you change theta by some amount, then the change in the unit vectors er and e theta can be written using again the ideas from calculus, where we know that change in function can be written as the partial derivatives um, of product of partial derivatives of the function with respect to independent variables which are changing and multiplied by the changes in those variables. So if you treat these unit vectors as functions of the coordinates themselves, then delta ei quite generally can be written as delta partial derivative of ei with respect to some coordinate, spatial coordinate xj, and of course multiplied by the increment in that coordinate delta xj. So if it means that if xj is changed by a small amount delta xj, then the change it produces in the unit vector ei can be written as the product of partial derivative of with respect to that coordinate multiplied by the change in that coordinate. So again here summation over j is implied, and because j is the repeating index on the right hand side. So I can just plug this delta ei in the above expression. So I have a general kind of expression for delta r written like this. Now notice two things. Both the terms, though they look very different, okay, in the sense that they have been given, they are coming from different sources. The first term is purely the effect of change in coordinates, whereas the second term is the effect of change in unit vectors. But if you look at them mathematically, they look very much similar in the sense that they involve a change in the coordinate direction, delta xi in the first one and delta xj in the second one. And while there is a unit vector ei in the first term, even the partial derivative of a unit vector, as I have already shown you with the cylindrical coordinate, that the partial derivative of a unit vector is itself a unit vector. So you should actually view the partial derivative del ei cap del xj as some quantity proportional to a unit vector. Okay, it may be exactly equal to a unit vector, it may be proportional to a unit vector, but so therefore here you may visualize some kind of a unit vector here. So if you look at it this way, then it means that if both the terms have very similar forms in terms of changes in coordinate and multiplied by the unit vectors, and of course there may be additional terms like xi in the second term. So it means that quite generally, if I want to write delta r, I'll write it as delta xi product of three things: the change in coordinate, the unit vector, and those extra terms that may arise as shown in the above example, that the second term may give rise to xi and maybe some proportionality constant due to the partial derivative. So it means that even if you ignore the fact that partial derivatives of unit vectors, you can treat them as simply equal to some unit vectors. Even then xi is the additional factor present there. So it means that all this tells me that delta r can be eventually written as delta xi, changes in the coordinates, and of course the corresponding unit vectors ei, and some scale. Okay, so these scales, now I hope you realize why they are entering into picture. That is because of the changes in the unit vectors, that's all, with the space. So in those coordinate systems where unit vectors don't change, for example Cartesian, you don't expect to get these scale factors, and you are very right. In fact, in Cartesian coordinate systems, the value of hi is 1. That means for all coordinates x1, x2 and x3 Cartesian, h1, h2, h3 all are 1. Okay, so delta r is in general hi delta xi ei. So this is very important. The displacement, infinitesimal displacement vector in general coordinates can be written as hi delta xi ei. This you need to remember. The background you may remember or may not, but if we remember this in our mind, that the displacement vector, the small displacement vector in space, for any arbitrary coordinate system, if you just remember this expression, you will do fine. Okay, you may or may not remember the background. Of course, the background is necessary to give you confidence that what you are stating, you know its roots and sources, but what you need to just remember is the final expression. So now there are three things: the scale factors, the slight infinitesimal changes in coordinates, and the corresponding unit vectors. So, as I've written, magnitude of displacement components. So, these are actually displacement components. Hi delta xi are the displacement components along coordinate directions. And as you can see, the magnitude is not necessarily equal to delta xi because of the scaling factors involved. So now the examples will make this further clear. If I am working with Cartesian, then delta r is just equal to delta x1 e1 delta x2 e2 plus delta x3 e3, because there are no change in unit vectors. In fact, e1 e2 e3 are in the next step written as ijk, and x1 x2 x3 are delta x delta y and delta z. So as you can see in this case, there are no unit vector derivatives, so therefore delta r can be simply written as reverting back to the indicial notation. For Cartesian, you can simply write delta r as delta xi and the product of the corresponding unit vector ei cap. So it means that all my scale factors from this basic expression of delta r for my coordinate system Cartesian, I can conclude that hi is 1. hi1 means 3 hi's, h1, h2 and h3. That means one associated with x, one associated with y, one associated with z direction. They are all unity. So all scaling factors are unity. Now if you come to cylindrical, the same picture slightly changes. Now I again start writing r for the cylindrical coordinates, and I have already showed, you can refer back to my probably third or second lecture where I have talked about cylindrical coordinates, and with the diagram I have shown that the position vector is in cylindrical has no theta component, and you can simply write it as r er plus z ez. Then delta r will be the delta of the two quantities, and which is then expanded. So delta r er plus r, delta of er, because unit vector er definitely changes, and plus delta z ez, because ez does not change. So we know that. So that's why there's only one radial unit vector change which needs to be accounted for. Now delta er can be written as der cap d theta delta theta, and we know already this derivative, so it comes out to be e theta cap delta theta, and then we substitute it back into our above expression, so we get the scale factors, and everything is before us just by comparing it with the general expression hi delta xi ei cap. So we find that this radial direction scale factor is 1, the theta direction scale factor is r, and the z direction scale factor is 1. So I have already circled these scale factors 1, r and 1. So it means that whenever I am going to take radial direction, the scale factor will be 1, theta direction scale factor r, and z direction scale factor 1. So this is what is finally written, that when we say I varying from 1, 2 and 3, so 1 would refer to radial coordinate, 2 to the theta coordinate, and 3 will refer to z coordinate, and the scale factor values I have already mentioned. Once the scaling factors for a coordinate system are identified, so the above exercise, the purpose of all this is to show you how to get scaling factors for a certain coordinate system. Because if you don't know the scale factors, then you can't write the del operator. The del operator requires these scale factors. So that is why all this business is all about. Okay. So once scaling factors for a coordinate system are identified, we can write the del operator, as I mentioned. So del operator in Cartesian comes out to be, we already know that, but now we know the background why in Cartesian it comes out to be like this and why it comes out to be in a different form for cylindrical. So the Cartesian and cylindrical del operators are clearly written here. So notice that for the cylindrical we have the scale factor r in the second term, which means the theta coordinate has got a scale factor h theta is r. So that's why the del operator, if expanded starting from the general definition, ei cap del over hi del xi, or rather ei cap del xi and 1 over hi, I should say. If I expand this, then I get these operators. Now come to using the del operator, right? So let us see how we can use the del operator. So the first thing that I demonstrate is gradient of a scalar. How we can take the gradient. So gradient is very simple. Since I apply the operator on phi, and phi being a scalar, so it is simply written as ei cap del phi del xi and 1 over hi. So ei cap upon hi, you can read it like this, ei cap upon hi del phi del xi. Again, remember to sum over the repeating index I. You must keep that in mind. Now there are some very basic uses of this concept of gradient of a scalar. Okay, so pay attention here to the uses that we are trying to point out here. To find rate of change of the scalar along a given direction, this is one use. That means if you have a flow domain, as I have indicated by my some smooth lines, and I am focusing on a point P, then at point P, suppose I am moving along this dashed line, which I am calling it as the direction M. So this direction is fixed. Okay, I am somehow interested in finding that if I move along this dashed line, which has a direction specified by the unit vector E cap M, then how fast my property phi or the scalar phi changes along this dashed line or direction, you can say. So this gives you a sort of directional derivative of phi. So we write it as d phi dm, that means rate of change of phi with m direction. And this can be written as the dot product of grad phi being a unique vector at point P, which is grad means gradient. Okay, so I'm just speaking in short terminology. Grad phi, we will call it as simply grad phi. So del phi or grad phi. Then if I get this value at point P using the definition given above, then that comes out as a vector. Okay, so now if I take the dot product of this vector with my unit vector E cap M, which is of course my choice because I'm interested in getting the space rate of change of phi along direction given by E cap M. So if I just take this dot product, then I get the derivative which I want, d phi dm. Okay, so this is one use of you can say in fluid mechanics, how to find rate of change of some scalar along a given direction. Now this may be useful if you are interested in knowing in the flow field in a specific direction the rate of change of the scalar quantities. And from here it is quite obvious that the rate of change is going to be smaller if you are not in the direction of grad phi. The grad phi vector will be having a unique direction at every point because it is defined as you have already seen, grad phi. So its value at a particular point will be having definite components along the various coordinate directions. So it will be a fixed direction vector. Okay, so grad phi direction, as I have shown, is not in general coincident with your direction of interest. So it means that once grad phi and EM are not aligned, then the rate of change will be always smaller in any other direction. It will be maximum if you move in the same direction as grad phi. So this is something important. We often say that grad phi gives a direction along which phi changes at the fastest rate. Okay, this I repeat. So grad phi gives a direction along which the rate of change of phi is maximum or the highest at that instant of time at a particular point in the flow domain. So it gives the instantaneous direction at a point in along which you will find that phi will be changing at the highest rate in space. Now another use is purely geometrical in nature. It is used to find unit normal vector to a surface. So suppose I have a surface in 3D as given by some scalar relation phi r, phi as a function of r is equal to 0. I have given a simple example, spherical surface, so x square y square plus z square minus r square 0. That is the equation of a spherical surface. So you can simply write it as a function phi x y z and equal to 0. Or you have a paraboloidal surface, so paraboloidal surface whose axis is coincident with the z-axis. So in Cartesian, so z is equal to x square plus y square, or if you arrange everything on one side, then again you can say that it is some function involving x, y, z, and this function is equal to 0. So when we have kind of surface for surfaces in 3D, they can be written as a some scalar function. So if you want to find out unit normal vectors on these surfaces, you can just find them as grad phi by mod grad phi. That means grad phi gives a vector along the normal direction, and to make that vector unit in magnitude, you divide it by the magnitude of grad phi vector. So this is the use of the del operator or the gradient of a scalar. Now I move on to curl and gradient of a vector. Okay, so curl and gradient of a vector. So curl operation is generally written as del cross A, and in language it is written as curl curl and A, and del cross A is then written as so I've done nothing magic here. The del operator is written in brackets first and then cross with the vector A. By now we are familiar how to write vectors and tensors, and I've already told you that if you use up one of the indices I in a particular vector or operator, then you have to use some other index for the other vector. So aj ej, and then notice how we start working with this kind of a operator. The first thing we do is that the partial derivative operator del xi, of course with the scaling factor hi, this partial derivative is first operated on the second vector, which is aj ej, and the cross product is left as it is, ei cross, for later on. Okay, we'll handle that cross product later on. So once you operate the derivative on aj ej, then in general, recognizing that ej can also change with the spatial coordinates, we will have two sort of quantities. So one is del aj hi del xi, or partial derivative of aj with respect to I, and scaling factor hi and ej, plus of course aj, and then the partial derivative of ej unit vector ej cap with respect to xi, and of course the scaling factor. So I'm just using a product rule, you can say, for the derivatives by recognizing that there are two quantities which can change with xi. So now del cross A has a very general looking form. Once this derivative is done, then in the last step we take the cross product. So naturally the ei cross ej. So therefore since cross products are not commutative, so you cannot write it as ej cross ei, because ei is coming from the left of ej. So it has to be written as EI cross EJ plus of course AJ, and then again, since the partial derivative of a unit vector will be some unit vector, of course that depends on the coordinate system, but it has to be a unit vector. So I write it as EI cap cross the partial derivative. So again, since the cross product is coming from the left, so the unit vector EI cap is kept on the left of the cross product here also. So for a general coordinate system, this is how the curl would look like, or del cross A. That means del cross A of a involving a general vector A in any coordinate system, you can finally arrive at this expression. Now you can simplify, because as I told you, most of the time we work with the orthogonal, almost 100% of the time we work with orthogonal coordinate systems and Cartesian and all. So we can see how we can reduce all this. So starting from the general expression for orthogonal systems, we can say that the first term having the cross product EI cross EJ, I've already discussed the cross product of vectors, so I can use the permutation symbol EIJK and EK. So I write the cross product by that in that notation. And second term, of course, I can't do anything, because unless I have a specific coordinate system in mind, I can write its unit vector partial derivatives. So I'll show that when I apply all this to specific coordinate systems. So this is all that I can do. And permutation symbol, for your remembrance, I am again mentioning it is +1 for cyclic combinations IJK and -1 for anticyclic IJK and 0 otherwise. So it means that you have to expand the first term by taking this into account. So you will basically always get 3 cyclic terms and 3 anticyclic terms, and that's all. Okay. And so there will be 6 terms in the expansion of the first term. वैसे तो देखा जाए तो फर्स्ट टर्म में आई भी रिपीटिंग है, जे भी रिपीटिंग है, के भी रिपीटिंग है. So in general, if there are 3 repeating indices, so for a 3D scenario, that makes it 27 terms. But 27 में से 21, I mean, it's a great and happy situation for us that 21 are actually 0. That is because of the fact that for any combination which is not cyclic and anticyclic, it is 0. Permutation symbol tells us that the cross product will not result. So therefore, you actually have to deal with only 6 and only 3 cyclic and 3 anticyclic. So no need to have a summation over I, J and K as far as the first term is concerned. Now look at the second term very carefully. For Cartesian systems, we know that there are no unit vector derivatives, so the second term is simply 0, and I have the first term only. And of course, in general, we have to sum it over I, J and K, but due to properties of permutation symbol, we have only 6 non-zero terms. Why? Because the permutation symbol E123 and E231 and E312 is +1, E213, E321 and E132, the anticyclic combinations, this is -1, all other are 0. So therefore, even if I sum over I, J and K, I will be only getting this expansion that I have written. I'll get only 6 terms, so I have directly written for these 6 indices only. That means the 3 cyclic ones, 1, 2, 3, 2, 3, 1 and 3, 1, 2, and then anticyclic ones, 2, 1, 3, 3, 2, 1 and 1, 3, 2. And so this is the result for del cross A. In Cartesian coordinates, you can replace x1, x2, x3 by xyz and e1 cap, e2 cap, e3 cap by ijk, and a1, a2, a3 by ax, ay, z. So you get the expression in Cartesian. Now notice that the above result is useful for expressing vorticity vector in 3D. Why? Because if you recall, when we introduced vorticity, we were doing it in 2 dimensions, and therefore we had only the third direction component of vorticity only. That means we had just the E3 term, okay, as the vorticity. But now we see that there are two more terms in the del cross A. So, and we have already shown you that since we are working with 2D, we have one component, and so therefore in 3D we have pairs of material lines in X, Y, Y, Z, and XZ planes. So those pairs of mutually perpendicular material lines will give rise to one component of vorticity from each plane. So, and it will be perpendicular to the plane itself. So therefore, the del cross A is exactly giving me that, because the one term which is along Z direction is exactly the same what I derived from first principles. So therefore, the other terms are perfectly what we want for a three-dimensional vorticity vector. So omega, the vorticity, we have now obtained a general expression for vorticity in three-dimensional flow domains, and this general expression, believe me, is really general, because you can use it to write vorticity either in Cartesian or cylindrical or any kind of a frame, because you are writing it in terms of a del operator, or what we call as the coordinate free form. That means omega is equal to del cross V does not rely or is not applicable to any specific coordinate system, rather it is applicable to a general coordinate system. Now let us look at cylindrical coordinates, how we can write del cross A in cylindrical. So again, two terms, so I can move a little bit faster now so that I can wind up my part 1 lecture. So term 1, I'm doing it explicitly for your understanding and benefit, but you are also quite capable of do all these things yourself by now. So since I have to sum over all possible cross product combinations, so as you can see that in the previous slide, though the I, J, K are repeating indices, but we know that ER cross ER and E theta cross E theta and terms like that will be 0. So that's why we are only considering whenever I and J are not same. Okay, so the summation over I and J is implied, but when we do it, then 3 of the terms out of 9 are actually 0, because you take the unit vector cross product with itself, so it will be 0. So you only end up with 6 of these terms. I'm doing it from the basics. I'm not going through the permutation symbol. You can very well do it through the permutation symbol also. But I'm trying to show that even if you're not comfortable with permutation symbol, you can even do it from the basic unit vector cross products also. So now the terms look like this. So each of these cross product of the unit vectors we can write using the right hand rule. So ER cross E theta is EZ, E theta cross EZ is ER, and EZ cross ER is E theta. So in cyclic order they always go like this. So term 1 becomes this, and term 2, now I'll show you how to handle this in cylindrical coordinates. So AJ EI cross del EJ cap del EJ cap del xi. So I should write it as either I should view it as a partial derivative del EJ cap del xi, and of course the scaling factor 1 over hi. So now we will recall that, though again you should be summing over j as well as I, because both are repeating indices, but since we know that the partial derivative only exists with respect to theta, so even if we sum over I, we will only end up with only one partial derivative, and that is with respect to theta. So that's why we fix I. Okay, we fix I as theta. So in the next step I have written AJ, and I is fixed as theta. So theta cap, E theta cap cross del theta of EJ cap, and of course the corresponding scaling factor is 1 over R. So we are now only requiring the summation of the repeating index j. Now again, as you know that even if you sum it, then sum means over r, theta and z. So out of this, the z unit vector doesn't have a partial derivative, so you just need to sum it over 2. That means j is r and j is equal to theta. So the first term, when I take j as r, so I'll get ar over r e theta cross, and since I'm talking of del er del theta, so del er del theta which becomes e theta, and then you have e theta cross e theta, so that term goes to 0. And the second term, when I take j as theta, will contribute, so a theta by r, and e theta involved in cross product with del e theta del theta. So del e theta del theta is minus er, so e theta cross r is e theta cross minus er. So as we know that er cross theta is e theta is ez, so e theta cross minus er is same as er cross e theta, so the result is e cap z. So the second term comes out as a theta by r ez. Now I would advise that while you are following what I am saying, but if you do it at just once, you don't need to do it even twice. I'm sure that if you do it once, it is enough, okay? Because these things are just for your understanding. These are not part of, I will not be treating it as part of my syllabus of the fluid mechanics as such, but this helps you to understand the various mathematical forms and equations and terms that you are encountering in fluid mechanics frequently, and how are these expressions managed in different coordinate systems. Your second mathematical sheet of theorems, identities and rules from vector calculus has actually, in that sheet we have actually given all these expressions, curl and everything is given. So from the point of view of examinations and usage, you are not expected to derive all these things again and again. This is just for, making you very strong and confident in the various mathematical tools and various mathematical ideas that fluid mechanics frequently uses. So you should be knowing the background. That's the idea. So now, so the second term I have shown it is equal to a theta by r e cap z. Okay. So if that is the case, then del cross a comes like this. Okay. So I can add term 1 and term 2 to get del cross a. So now I come to one of the last topics in this part 1 lecture, which is already close to 50 minutes now. So it's like one period coming to an end. So I'll try to do this in the remaining 5-10 minutes. So gradient of vector. Now this is something totally new, because up till now you might have heard about gradient of a scalar, but yes, we can define gradient of a vector also. How we define? Notice something very interesting. Del A. So there's no dot or cross in between. So when you have two vector kind of things, and you remember in my 5th lecture I talked about these things. I talked about a dyadic product, right? Dyadic product. So I had said that AB, vector AB, simply written without dot and cross, is actually a dyadic product, and it gives you a tensor of rank 2. So the same is the story here. The vector operator del without any dot or cross operated on A, as you can see, using indicial notation. I have done this in your straightforward steps. So as I have indicated, since you start getting dyadic products of the unit vectors, so this obviously hints that the final result should be coming out as a tensor. So when you take a gradient of a vector, it gives you a tensor of rank 2. When you take a gradient of a scalar, it gives you a vector. So it's like increasing the order of complexity, scalar to vector, vector to tensor. Okay, so gradient keeps on increasing the order of complexity. So now the terms look like this, and finally I've arranged them in this form. So gradient of a vector in this is all given in my algebra calculus sheet also, so you already have that. And so I am going a little bit fast now. So you can notice that both the terms have a dyadic product. The first term obviously is simply directly a dyadic product, ei cap, ej cap, and even the second one, because the partial derivative, as I said, of a unit vector with respect to any coordinate direction is itself a vector. So again you can view it as a vector in this expression. So again a dyadic product there. So it means that RHS is a tensor of rank 2. Now for Cartesian coordinates, again we know this, all these things, scaling factors and are unity, and partial derivatives of unit vectors are 0. So you are left with only first term del aj del xi, with hi becoming 1 and ei cap ej cap. So this is the gradient of a vector. Now in general, gradient of a vector is a tensor of rank 2, and what I've done is that I've given a general kind of a symbolic representation, just as I did for the infinitesimal displacement vector. Remember, delta L delta R is equal to hi delta xi ei. In a similar way, when we write this gradient of a vector, since it comes out as a tensor of rank 2, and you know that a tensor representation, as I already talked about in my earlier lecture, is simply a component and a dyadic product of unit vectors ei cap ej cap, two directions involved. So this is a very general way of representing this tensor, gradient of a vector, and this gij ei cap ej, and obviously summation of over repeating indices has to be kept in mind. So there is another related tensor. Now this is the gradient of a vector. Now there is another related tensor to gradient A, gradient of A vector, that helps in expressing local strain rates, है ना, जो हमने earlier अपने lectures में lecture 2, 3, 4 वगैरह में देखे थे, local strain rates जो हमने 3D में भी extend किए थे. Remember, epsilon xx, epsilon yy, epsilon zz, and the 3 shear ones. Now all those can be sort of put under one roof and umbrella, or in a general coordinate system in 3D. If I define another velocity gradient, another gradient of a vector, so the gradient of a vector gij eij is already there, gij ei cap and ej cap. So if I define another related tensor, why I am saying related, you will soon see. This is grad A and with a subscript T. Okay, so this is read as transpose of grad A. Okay, so इसको जब पढ़ना होगा, so we will not say grad A T, we will say transpose of grad A. Okay, so grad A is already defined, or gradient of a vector A is defined as gij, a tensor of rank 2, gij ei cap ej cap, and its transpose is defined as gji ei cap ej cap. Okay, so please make a note of this. So the components are just transposed. So gij were the components, so now I take the components as gji. The unit vectors are kept the same. This is important. Okay, ei cap and ej cap. It's not that when you take the transpose, you also interchange the unit vectors and start saying ej cap, ei cap. No, the dyads are still written the same way, and the transposed sort of gradient of a vector is written as with the same components gij's, but interchanging their indices. So it means that if the first component, for the first component it won't matter, they would be same, but whenever I is different from j, for example, consider I1 and j2. So while the gradient of a vector has the component g12, the transpose of the gradient of the vector has the component g21. Okay, the same 1 2 component is g21. So the values are just you know transposed, you can say, or the if I take these components and form a matrix, then the matrix is transposed. That is the meaning. So I'll show you that actually the transpose, you don't need to estimate the components of the transpose. They are normally found from the Gij itself. So for example, in Cartesian, the gradient of a vector is written as del, अभी दिखाया था हमने पिछले slide में, gradient of a vector is del aj del xi ei ej. So I already have the Gij components. So Gij is this. So therefore I can directly write grad a t, or transpose of gradient of the vector a, is equal to, now in order to write Gji, since Gij is del xi of aj, so Gji would be del xj of ai. Okay, so del ai over del xj, and the same diodes as I've mentioned, ei cap, ej cap. So this is these are the gradient of a vector. The two gradients that we can talk of, one is gradient of a, other is its sort of transpose, you can say. So for cylindrical coordinate systems, I can just now, to conclude, I can just give you a hint that starting from the general expression, starting from general relation, gradient of vector a, which is this, we can obtain the expansion of right hand side for the cylindrical coordinate systems. So you can just work out these two terms, term 1 and term 2, in your cylindrical coordinate system, and once you get that, you can finally obtain the components Gij. That means you can after the expansion is done in cylindrical coordinates, you can find out what are the expressions for grr, gr theta, grz, and so on, in terms of these vector components and partial derivatives. So this is left as an exercise for you to do yourself. I'll give it in the notes in the PDF form that I'll be passing on after these lectures, so you can confirm your answers, but right now you are expected to do it yourself for the cylindrical coordinate and get these components Gij. Now once Gij are known, you can just get the transpose also, because it's very easy. The same components are written with I and j interchanged, okay, in the transpose gradient of the vector tensor. Okay, so now with this background, we can just conclude this rather lengthy 1 hour lecture, and with this background we can express the local strain rates and local rotation rates in coordinate free forms, which are valid for both 2D and 3D flow fields. So this is something very, very attractive for us, that we have with this background. I'll show it, of course, in the coming lectures, subsequent lectures, how we can use this background to express local strain rates and as well as local rotation rates in either 2D, 3D and in coordinate free form. So there are two distinct advantages. I am not sticking to any particular coordinate system. Remember, जब फंडामेंटल से फर्स्ट प्रिंसिपल से हमने डिराइव किया लोकल स्ट्रेन रेट और रोटेशन रेट, then we had to take help of some Cartesian coordinate system, और हमने मैटर को सिंपल रखने के लिए 2D में भी किया, because we needed some physical conception of these local strain rates using material line kinematics. उसको यूज़ करते हुए हमने रोटेशन और स्ट्रेन का बेसिक आइडियाज़ डेवलप किए. But once those ideas are there, they are good enough, and now we need a tool where I can directly jump onto my 3D flow situation, and not only 3D flow situation, I should be able to express it in any coordinate system. मेरा कोई भी coordinate system हो, my physics should be the same. My physics should be retained in any coordinate system. So I need some kind of a expression for local strain rate and rotation rates in this, using all this, so that coordinate free forms are there and they apply to both 2D and 3D. तो ये जो लेक्चर में जो 10 ये जो ऑपरेशंस बताए गए हैं यूजिंग डेल ऑपरेटर्स, दीज डेल वाले जो ये ऑपरेटर्स हैं, चाहे वो ग्रेडियंट ऑफ अ वेक्टर हो, चाहे वो कर्ल ऑफ अ वेक्टर हो, एंड इवन इफ इट इज these operators that I have talked about here. तो ये हमें किस तरह से लोकल रोटेशन रेट्स और स्ट्रेन रेट्स दे सकते हैं, तो ये हमें आगे हम देखेंगे. So with this I would like to end this lecture, and the second part deals with only one operation involving the del vector, so it will be a much shorter lecture. I am putting it on record in the same session, and it will be available, both the lectures will be available to you in one go. So thank you very much.